The foundation of quantum mechanics is explained by the following experiment. Suppose we have a wall with two holes. Suppose we shoot marbles at it, one marble at a time. Behind the wall, we have a cloth. Each time a marble hits the cloth, we mark where it landed. As marbles hit the cloth in the same spot more than once, we mark the red mark darker. Some marbles make it through the holes by bouncing off at an angle. But most marbles that make it through the holes continue in a straight line. After a while, there will be many red marks on the cloth. The darkest red marks will be directly behind the two holes. Now suppose the two holes are very narrow. Suppose the marble is very small. Now the result is very different. All particles in the universe produce this striped pattern, provided that both they and the holes are small enough. No matter how many times we repeat this experiment, and no matter what type of object we use to replace the marbles, the result is always the same. Only one known phenomena can explain this result. Waves. When a wave passes through a hole, it spreads out on the other side. If there are two holes, two waves are produced. When you have two waves, they interact with one another. It's not just that we ourselves do not know the outcome until we look. It seems that even the universe itself does not know which object is standing up and which object is knocked down until we actually open our eyes and observe the results. To explain why this is the case and what this means about the fundamental nature of our universe, let us talk about spin. The direction of the spin of a particle can be described by an imaginary arrow. Particles spinning in opposite directions will have their arrows pointing in opposite directions. Particles are too small to see the spin directly with our eyes, but we can build detectors which tell us if the spin is in the direction of the red plate or if the spin is in the direction of the blue plate. Suppose we think that we already know the spin of a particle ahead of time, because we have measured it previously and we line up the detector with this direction. The detector will always give us the same result we measured previously. But if the spin we measured previously is not in the same direction as the detector, then the act of measuring the spin ends up changing it. It is not possible to simultaneously measure the spin of a particle in more than one direction at a time. If we want to know the direction of the spin in the horizontal direction, then we need to rotate the detector. But why does this mean that the universe does not know what an object is doing until we observe it? The answer lies in the fact that we can produce pairs of particles that always spin in opposite directions. If the two detectors are aligned in the same direction, then when the spin of one particle is measured to be towards the red plate, the spin of its partner is always measured to be towards the blue plate. This is true 100% of the time. This is still true the vast majority of the time, even if we offset the detectors by 45 degrees. We know this based on experiment. If we offset the detectors by 45 degrees, then when the spin of one particle is towards the red plate, the spin of its partner will be towards the blue plate, the vast majority of the time. Suppose the two detectors are perfectly aligned with each other, and they are both in the diagonal position. Does the universe know ahead of time that the first particle will be measured to be towards the red plate, and that the spin of the second particle will therefore be towards the blue plate? If the universe knows ahead of time that the spin of the second particle will be towards the blue plate, then this means that the universe must know that the spin of the first particle will probably be towards the red plate, even if we rotate its detector by 45 degrees, either into the vertical position or into the horizontal position. Therefore, if the universe knows the results in the diagonal observation ahead of time, then the universe would also know that if one detector will be rotated into the vertical position, and the other detector will be rotated into the horizontal position, the two particles will still probably be spinning in opposite directions. But when we actually do the experiment, this isn't what happens. When the two detectors are offset by 90 degrees, there is no correlation between the measured spins of the two particles. When the two detectors are offset by 90 degrees, the spins of two particles are just as likely to read in the same direction as they are to read in opposite directions. Therefore, if we start out by assuming that the universe knows ahead of time what the measurements will be, this leads to a contradiction. Assuming that the universe knows the answers ahead of time implies that most of the time, the measured vertical spin of one particle must be in the opposite direction of the measured horizontal spin of the second particle. But we know that this is not the case. The apparent implication is that the universe cannot know ahead of time what the measurement of the spin will be, and the universe makes up its mind only when the spin is actually observed. The apparent implication is also that when the spin of one particle is measured, it sends an instantaneous message to its partner to spin in the opposite direction. If each particle makes up its mind about what direction it's spinning only when it's observed, then we need this instantaneous message from one particle to the other in order to guarantee that the two particles will always decide to spin in opposite directions when the detectors are aligned. This is true no matter how far apart the two particles have traveled away from each other. Even if we wait until the two particles are on opposite sides of the universe before we make our observation, this instantaneous message still seems to occur. Until we observe the particles, their spins are nothing more than probabilities. But we need to observe only one of the two particles for both of them to simultaneously decide in what direction to spin. If everything in the universe is made out of these particles, including the detectors themselves, then the detectors are also nothing more than a probability until they are observed. According to the mathematics describing the probabilities of the particles, passing through the detector is not what causes the particles spin to decide to spin in one direction or the other. Passing through the detector entangles the detector to the particle in the same way that the two particles are entangled to each other. The moment we look at the detector, it seems to send an instantaneous message to the particle so that the detector's measurement will agree with the spin of the particle. This is the same way in which the two particles seem to send instantaneous messages to each other. There are many possible explanations as to what's actually happening and how to interpret these results, and this is a matter of considerable debate. But if we really do have these types of instantaneous messages, which are faster even than the speed of light, then this creates an interesting situation with Einstein's theory of relativity. According to Einstein's theory of relativity, different observers will disagree about which of two events happened first, and no observer is more correct than any other. From one observer's point of view, the right particle was observed first and caused the left particle to change its spin. From another observer's point of view, the left particle was observed first and caused the right particle to change its spin. Therefore, we can't know which of these events is the cause and which of these is the effect, since both points of view are equally valid. In fact, according to quantum mechanics, we can't even know which particle is which. Suppose we have two particles in a container. Each particle does not have its own separate probability wave. There is only one probability wave, which describes the probability of measuring the two particles in every possible combination of positions. The probability that particle 1 will be in one position and that particle 2 will be in another position is exactly equal to the probability that the two particles will be in the swapped positions. Therefore, we cannot know if a particle we're observing is the same particle we measured earlier. If we think of our container as the entire universe, then this would imply that the universe consists of just one probability wave, governing the probability of all the particles in existence. But if we ourselves are made out of these exact same particles, then why is the act of us observing something so fundamentally different from everything else in the universe? This is one of the greatest unsolved scientific and philosophical mysteries of all time.